Okay, let's dive right in. Welcome to your AI Tech Pathway. If you are currently working through the Deep Reinforcement Learning course, consider this explainer your overview of the critical tutorial session, focusing specifically on Q-learning. We're going to break down exactly how artificial agents actually learn to make decisions, and we'll transform all that abstract math into some real practical intuition as we go.
Here is the blueprint for our journey today. We're going to meet the grid world robot, unpack Q values and policies, compare Monte Carlo against TD learning, scale things up with neural networks, stabilize our AI agent, and finally, fix Q value overestimation. Let's get to it.
Section 1. Meet the grid world robot. We really need to anchor all this heavy theory around a simple visual metaphor. So think of a basic robot trying to navigate a grid world. This is going to be our testing ground. Now, what's really fascinating is how we formalize this robot's world into something a computer can actually process. An MDP basically means the agent takes an action from a given state, the environment transitions based on its own internal dynamics, and then the agent gets a reward. It's the fundamental loop of all reinforcement learning. So, let's establish the rules of our little grid world. Our robot is looking for a gem in the top right corner, which gives a +1 reward. But it desperately needs to avoid the lava pit in the middle because that carries a -1 penalty. To do this, it has a basic toolkit of 5 specific actions. It can move up, down, left, right, or just stay put. The ultimate goal here? Maximize that expected return over time. Section 2. Unpacking Q values and policies. To actually maximize those rewards, our robot obviously needs a brain. This is where value functions and policies come into play. The crucial distinction to make is that the Q function gives us slightly more granular information than the standard value function. A value function just looks at a state and says, hey, how good is it to be here, assuming I follow my current policy? But a Q function probes exactly how good an immediate action is right before we commit to it. It's basically asking, if I'm right here and I take this specific action, how good is my future going to be? And if you're ever wondering whether an action is better than your average move, the advantage metric tells you exactly that. It's literally just the Q value minus the value function. For a perfectly optimal policy, all your suboptimal actions will have a negative advantage, and the absolute best actions will just have an advantage of 0 because, well, they are the baseline. Think about how a dynamic programming approach handles the famous Bellman equation here. Imagine an entirely empty grid. We start at the end, the terminal states, where we know for sure the reward is +1 or -1. Then, using the Bellman equation, we step backward, calculating the max future value for the neighboring squares, and then their neighbors. We're essentially stitching our robot's optimal past experiences together by propagating those rewards backwards across the entire grid until everything converges. Section 3. Monte Carlo versus TD. We now face a really critical learning choice for our robot. Should it learn from a complete lifetime of actions, or should it learn step by step? We have 2 major learning paradigms going head-to-head. On one hand, there's Monte Carlo. This requires full episode rollouts. The robot plays until it either wins or dies, tallies up all the rewards, and then learns. On the other hand, we have temporal difference, or TD learning. TD bootstraps. It takes just a single step, guesses the value of the new state, and updates its knowledge immediately based on that guess. When weighing these options, you run into a classic machine learning dilemma. TD lowers variance beautifully because it avoids those long, noisy, unpredictable rollouts. But it introduces high bias because it's relying on its own incomplete value estimates. Monte Carlo, meanwhile, has 0 bias since it uses actual real-world returns, but the variance is massive because so many random things can happen over a long trajectory. Now, tabular tracking, literally keeping a spreadsheet of every state in action, works great for a tiny 5x5 grid, but let's pause for a second. How on earth do we handle the infinite continuous possibilities of the real world, like, say, navigating an actual self-driving car? That brings us to Section 4, scaling with neural networks. To conquer massive environments, our robot needs a serious upgrade from a simple spreadsheet to a deep neural network. We have to transition from tabular Q-learning to parametric Q-learning. By plugging a neural network into the equation, we no longer need to memorize every single possible state. Parametric Q-learning lets our AI look at a completely new, unseen state and mathematically guess its value based on its semantic similarity to past experiences. It's a total game changer because it allows for generalization. Section 5. Stabilizing the AI agent. Because bringing deep learning into the mix definitely isn't free. Scaling up introduces some nasty bugs and instabilities into our robot's brain, so we need some specific tools to keep it on track. To do this, we rely on 5 critical engineering fixes: replay buffers, target networks, semi-gradients, gradient clipping, and Huber loss. Without these, your neural network is likely going to hallucinate, forget everything it knows, or just completely crash during training. Let's look closely at a couple of the most important ones. The replay buffer is absolutely fascinating. It makes sure our robot doesn't just overfit to the very last thing it saw. Imagine if you only learned based on the last 5 seconds of your life. You'd be heavily biased. A replay buffer stores individual transition snippets and forces the AI to randomly sample from its entire history. This breaks temporal correlations and drastically improves our sample efficiency. Then we have target networks. When an AI learns, trying to update the Q network using that exact same Q network to guess the future, well, it's like a dog chasing its own tail. To fix this, we implement a separate target network. We use a stop gradient to give the neural net a stable, frozen goal to regress toward, and we slowly update that target over time using something called polyact averaging. Section 6. Fixing Q-value overestimation. Because even with those engineering fixes, there's a hidden mathematical trap that causes our robot to become wildly overconfident. Here is the really insidious problem. Because the Bellman equation always dictates taking the maximum future value, any random noise or modeling error inherently gets amplified. Even if the noise is completely neutral, zero mean, taking the maximum mathematically shifts it positive. And this compounds over time, causing the AI to severely overestimate how well it's actually doing, which can completely ruin the policy. So how do we fix this massively compounding math error? Well, the surprisingly simple solution is an ensemble size of exactly 2 networks. This clever technique is called double Q learning. By maintaining a critic ensemble of 2 separate networks initialized just slightly differently, they're going to have different errors. When it's time to evaluate a state, we consult both networks, and we always trust the lower, more pessimistic estimate. Taking the minimum like this completely neutralizes that positive overestimation bias. We ground the robot back in reality, stabilizing the whole learning process. And that brings us to the end of our foundational Q-learning overview. As you take these RL building blocks, from the Bellman equations to replay buffers and double Q-learning into your own AI tech pathway, the real question is, how will you harness them to solve the messy complexities of the real world? Keep experimenting, keep building, and use this structural intuition to push your projects to the next level.